everyone. I hope you're having an amazing time here at PyLadies Con. Our next speaker is Jessica Ertel, presenting Building Trust in the Restoration Movement with Python, AI, and Satellite Data. Jessica is a data science manager at the World Resources Institute, where she applies artificial intelligence and remote sensing to monitor environmental restoration at scale. Jessica has over a decade of experience bridging technical, operational, and strategic roles in the environmental sector, including forestry, renewable energy, conservation, and urban water management. This talk will showcase how her work combines Python's rich ecosystem of data science, geospatial, and AI machine learning libraries to monitor, report, and verify environmental restoration activities. Take it away, Jessica.
Hi everyone, my name is Jessica Ertel. I'm a data science manager on the restoration monitoring team at the World Resources Institute, based in Washington, D.C. Our team develops computer vision applications for monitoring forest and landscape restoration around the world. I'm excited to share the ways in which we're using technological innovations like Python, AI, and satellite imagery to build increased trust and transparency in the restoration movement. Before I jump in, this is an outline of the topics that I would like to cover today. I'll start by grounding you in the challenge facing the restoration sector today. Then I'll share some background context about how WRI is operating in this space and how our team is designing a digital monitoring, reporting, and verification system to enable greater transparency and efficiency in the field. Once you have the background context, I'll delve into the juicy part, which is the technical components of our ecosystem, and I'll discuss how we're using different Python frameworks for data capture, processing, storage, analysis, visualization, and interaction with our various platforms. The meat of the presentation will focus on this section, and I'll break down some of the steps in our MRV pipeline to give you a better understanding of how Python operates as the backbone of this restoration monitoring ecosystem. We face a layered challenge to building the restoration economy. The first layer of this challenge is the funding gap, where financiers like private investors, philanthropies, and development finance institutions struggle to identify the most opportune investments. And where investments are being deployed, we see that they're not always effectively reaching the communities and farmers that understand local realities and have the greatest potential for impact. Tightly connected to this is the lack of standardized and transparent systems for monitoring, reporting, and verification, or MRV, of restoration activities. Without a standardized system for tracking results and sharing progress, it's difficult to understand and forecast whether a project is actually on track to meet targets. There's widespread recognition that field-based methods are very expensive due to high costs for data collection, on-site visits, dedicated equipment, particularly in inaccessible areas. These costs can be a significant barrier, especially for early-stage, small-scale projects. All of these challenges function to create a massive scalability issue. Where funding is bottlenecked, we can't connect investments to outcomes on the ground, and it's prohibitively expensive to do so for potentially high-impact interventions. The restoration team at WRI launched the TerraFund program in 2022 with the goal of accelerating locally led forest and landscape restoration. We source high-quality projects, we finance those projects with grants, loans, and equity, and, the focus of today's presentation, we monitor those projects for 6+ years using state-of-the-art artificial intelligence and high-resolution satellite imagery under an advanced digital MRV system. Since 2022, we've channeled around $32 million to over 200 different projects in Africa. We see a huge opportunity to leverage these digital innovations to address many of the challenges that I laid out on my previous slide. If you're not familiar with it, digital MRV involves the use of sensors, satellite data, AI models, and complementary field-level verification tools to build a transparent, traceable record for restoration projects. And this kind of information can establish a foundation of credibility, increasing trust among investors and donors. Simultaneously, it can also help project developers engage in adaptive management practices to ensure that their interventions are successful at project conclusion. Even within the field of digital MRV, we're seeing huge advances in what we can measure remotely, particularly due to the availability of higher resolution data, compute resources, and the launch of geospatial foundation models. Back in 2015, Collect Online was released as a sample-based tool where an individual could manually label trees in an image. If we were to use this platform to monitor our entire TerraFund portfolio, it would take an individual at least 10,000 hours. The rest of this timeline is showcasing several different data products that WRI has released since then or co-developed in collaboration with academic partners and other tech companies. By this year, in 2025, we're now using 30 centimeter resolution imagery and automating a tree count across all of our projects. Using a method like this to monitor our portfolio cuts us down to 80 hours. Let's chat a little bit about our tech stack. We combine Python's rich ecosystem of scientific computing, geospatial, and computer vision libraries, as well as various AI and ML frameworks to power our digital MRV system. Using Python in our tech stack enables us to process and store high resolution more efficiently, design tailored pre- and post-processing steps, and integrate with cloud infrastructure. But most importantly, it helps us connect everything in an automated manner and establish modular, reproducible workflows. For the purposes of this presentation, this is a grossly oversimplified diagram of our ecosystem and remote sensing workflow for generating tree count, which is an important indicator of progress on a restoration site. On the left, you can see we have a mobile data collection app called Flority, which is used for capturing field data such as site reports about our areas of interest and tree planting activities. This allows us to compare on-the-ground reported information from our project developers to our remote sensing derived data. Automated QA/QC workflows ensure that this data feeds into our platform and dashboards in a standardized way. The diagram on the right shows an abbreviated workflow for producing a remote sensing derived tree count for our projects. Each step is illustrated in the green box, with some example outputs below in the yellow boxes below. We start with an initial project evaluation that allows our team to identify if project characteristics are well suited for remote monitoring and verification. If so, we then move on to acquire imagery and run inference to derive tree count. Finally, this information is aggregated and displayed on our TerraMatch platform. So using Python, we can gather data through multiple APIs using the Python's request library. We can store intermediate and final outputs on AWS using Boto 3, which is the AWS software development kit for Python. And we can perform various data cleaning, validation, and analysis using NumPy, GeoPandas, GDAL, Rastereo, many of the other libraries referenced on my last slide. We've also enabled automatic syncs with Asana's API to help internal team management. So as you can see, Python acts as the connective tissue between each of these steps. And now I'll dive into the details for the 4 steps in our tree count data production pipeline. Step 1 is a project evaluation step, where we have designed a rule-based decision support tool to determine, based on the conditions on the ground, if a project is a suitable candidate for a remote sensing technology. On the rare occasion that a restoration strategy or land use type isn't easily detectable with remote sensing, it's really important to flag. This preliminary step helps us ensure that we're spending resources and time appropriately. The decision tool queries API feeds to gather data about restoration strategy, baseline conditions, image availability, slope, and many other characteristics about the project. Using pandas and NumPy, we perform cleaning and apply a decision logic. Using a config file allows us to experiment with different thresholds and criteria related to what defines a best quality image or an ideal baseline condition for our modeling pipeline. Ultimately, we're presented with a suitability score that determines the priority and timing for data production for that project. Step 2, we've developed an automated pipeline for querying and ordering Maxar imagery in order to retrieve the highest quality scenes within a defined time frame and within the exact project boundaries. These workflows ensure that our orders meet API specifications so our requests are not bouncing back. 2, that we're not purchasing imagery where we don't really need it. And 3, that we're only purchasing images that satisfy the requirements of our model inference stage. This Maxar tooling, the API tooling, is actually used at various moments within our data production pipeline. So we've turned this into a Python package that actually meets the different use cases across our team members that are either working with imagery metadata or placing orders. Once we have imagery, step 3 involves running the tree detection inference pipeline to get an accurate count of trees and saplings within our area of interest. Our team is using Dino v3 to develop an object detection method for associating an input image with the location of a tree. So as you can see in the image on the right, these trees are delineated in red bounding boxes. Dino v3 is a state-of-the-art computer vision model that's trained with self-supervised learning and produces high-resolution visual features. Using a foundation model like Dino v3, which is not specifically tailored to any type of image modality, enables data analysis across multiple satellites without the need to build a customized model. So rather than creating and fine-tuning separate models for each of our remote sensing data sets, we can rely on a single one. So I'm mentioning this with a nod towards the future of DMRV, where we can now rapidly accelerate our ability to deploy models across diverse Earth observation tasks. Back to our example, we are currently using Dino v3 to perform tree detection. And so in this stage, we're using Python to initiate a GPU EC2 instance, run model inference on the acquired images, and then produce as an output a harmonized tree count for each of our projects. The final step I'd like to discuss involves publishing all of this information to our TerraMatch platform so that it can be accessible to investors, donors, project developers, and partners. We use a Python-based aggregation script to compute and validate these indicators, format them according to the product API specifications, and then, patch them to the platform for use in our dashboards. We also use Asana's Python API to update tasks in our team's data production Asana board. So once an interim or final output is placed on an S3 bucket, the task is automatically updated. This gives us real-time insights into the status of each project and helps other teams stay up to date on our work. So these are the 4 high-level components of our DMRV system that I wanted to touch on to give you a flavor of how Python has helped inform our work. Python is not just one piece of our stack. It's the backbone that allows the scientific and engineering systems to talk to each other, whether we're calling APIs, processing imagery, pushing results to TerraMatch. Python glues together the scientific computing, geospatial, and AI components that make our MRV process scalable. One of my favorite aspects of working at WI is that we have a commitment to developing open source public goods. This means that all of the code that I referenced today is publicly available on GitHub repositories, which I'd highly encourage you to take a look at. Thank you for the opportunity to present as part of the PyLadies Conference 2025. I look forward to hearing your questions and welcome you to reach out if you're interested in learning more. Thank you.
Thank you, Jessica Ertel, for showcasing the important work that you do. It's amazing to hear just how far the advancements in digital MRV has come since 2015. I hope you all enjoyed that. I certainly did. Let's give a round of applause to Jessica and stay tuned for more insightful talks.